Okay, so I'm going to put up some terms here. Convergent, Cauchy, and bounded. Okay, so which imply which?
Conversion implies Cauchy.
Convergent implies Cauchy. Okay, what about Cauchy implies convergent? No.
Sometimes. I mean, sometimes.
Well, not automatically, right? Yeah. If your space is complete, then yes, right? Or rather, that's the definition of being complete, right? If all the Cauchy sequences converge, then it's complete. What about bounded? How does bounded fit into this? Does convergent imply bounded? Sure, right? Because convergent means that you can, that there's some point, and you can make everybody as close to that point as you want, right? So past a certain time, the tail is in here, right? The tail is going to be in your neighborhood, and then outside of it, there's only a finite number of the head of the sequence is finite, right? So you can definitely bound the head, and then the tail is bounded, right? So definitely convergent implies Cauchy. I'm sorry, convergent implies bounded, right? Convergent implies bounded. What about Cauchy? Does Cauchy imply bounded? It actually does. It actually does. So I think we showed this last time, right? That right, because what Cauchy means is that the diameter of the tail becomes arbitrarily small, right? The diameter of the tail becomes arbitrarily small. So same sort of thing, right? If the diameter of the tail is less than 1, then you know that the tail is bounded, and then everything else is bounded as well. Yeah. Okay, so yeah, so Cauchy implies bounded. What about bounded implies either one of these, Cauchy or convergent? Does bounded imply convergent? Can you think of a bounded sequence that does not converge? Right?
-1 to the n.
-1 to the n. So yeah, just bouncing back and forth. -1, 1, -1, 1, -1, 1, -1, 1, right? That's a bounded sequence, but does not converge, right? Similarly, it's a bounded sequence, but it's not Cauchy, right? So bounded does not imply Cauchy, also does not imply convergent. Okay, and that's where we're going to start from today. So I don't know if I don't know if this thing is useful at all, but I'm going to erase it. Julia, is it okay if I erase it? Yeah. It's okay. So so today we're going to start off with so-called monotonic sequences. Monotonic sequences, right? So yeah. So here's the definition, right? You have some sequence, right? And then we're going to say the sequence is monotonically increasing. If what does that mean? You can tell me. I have no doubt. Paul, go ahead.
Like there's an order like between any two elements in the sequence. There is only one order.
Yeah. So basically, the way to say it is that for every n, say Sn is less than or equal to Sn plus 1, right? For every n in n, Sn is less than or equal to Sn plus 1, then we call S of n monotonically increasing. Okay. So if no matter what time you choose, your successor is bigger than you, then your monotonically increasing function sequence, and you know, if you change the order, then it's monotonically decreasing. So, right. So similarly for decreasing. Okay. And the theorem that we're gonna, so there's this theorem called the monotonic convergence theorem or sequence theorem. Monotonic sequence theorem that says the following. If Sn is monotonic, so you have a monotonic sequence, then Sn converges if and only if Sn is bounded. Okay, so for monotonic sequences, boundedness is the same thing as convergence. Boundedness is equivalent to convergence. You've probably seen something like this before. How many of you have seen this before? All of you. You should have. You should have seen it in Calc 2. Right? The picture is, right, you've got a sequence that's monotonic, let's say monotonic increasing, right? And it's got an upper bound, right? And basically the existence of that upper bound forces the sequence to converge, right? Now, you couldn't prove that back in Calc 2, but we can do it now, right? And what are we going to use? Take 10 seconds and write down some idea, some concept that will be relevant. Okay, anybody want to say, maybe turn to a neighbor and tell them what concept you're thinking of? Concept, theorem, axiom. Okay, I'm back. Okay, what do people say? Anybody? Nope? Yes?
I had a question.
Yes.
Are the terms of the sequence, are they real numbers?
Yes, I'm sorry. Yes,
Okay.
we're in R. Sorry, yeah. So we are actually when we're talking about monotonic sequences. Yeah, so this is in R. Yeah. Okay. Now go ahead.
The least upper bound property.
Least upper bound property, right? Because you've got these guys here. You've got this set here, and it has a least upper bound. It has an upper bound, and so it has a least upper bound, right? So what's the point, right? Right. So the point is that okay. So we only need to prove one direction, right? Because the other direction we already know, right? So let's prove the converse direction, right? Sn bounded is the same thing as saying that there exists a set of points as an upper bound, and then there must exist a least upper bound. Right? There exists a least upper bound of the set of points. Right? Let's call it M. Okay. Maybe M is not good because I already used M. Call it S. Okay. So there's a least upper bound. Call it S. And then we want to show that the sequence converges, right? Convergence means that given any epsilon, we can find a time past which everyone is within epsilon of S, right? We can find a time past which everybody is within epsilon of S. So you say, okay, well, so here's the picture, right? Fix an epsilon, fix an epsilon, right? How do you know that there's going to be some time past which everybody's inside that neighborhood? Can anybody see that? Can anybody explain that? How do you know that? Right. So here's the least upper bound of these values, right? Right. The least upper bound of these values. How do you know that there's some time? Right. In the picture, it's obvious, right? After some time, everybody's inside there, right? Anybody? One thing you can do is you can go by contradiction. You say, so, right, we want to show that given any epsilon, there exists a time past which the distance of S of n to S is smaller than epsilon. Okay, so fix epsilon, right? Fix epsilon. We know that there must be somebody inside there, right? If there's nobody inside that, if there's nobody in that range, then this wasn't the least upper bound, right? But this we've done this sort of game before, right? This guy, if there's nobody inside that neighborhood, then S minus epsilon is an upper bound that's smaller than your supposed least upper bound, right? So fix epsilon greater than 0. There must be some Sn naught that's bigger than S minus epsilon, right? Otherwise, S is not the least upper bound. Right? So we know that there's some n naught, right? There's some n naught where you're inside that, where you're bigger than S minus epsilon. But this is an increasing function. This is an increasing sequence, right? So after that, you're always bigger than that, right? And S is the upper bound, so you can't be bigger, right? So for all n bigger than n naught, Sn is bigger than Sn naught, right? Since it's increasing, right? And of course, it's less than or equal to S because this is an upper bound, right? Right. And so that Sn, that tells you that Sn, lies between S minus epsilon and S plus epsilon. Right. So everybody beyond that point lies in between those bounds. Okay. Anyway, all we're saying is that at some point you got to have somebody in there. And then past that point, everybody's still in there. Right? That's this is. It takes a lot of words, but the idea can be easily seen. Okay. Any questions? Any questions? Okay. Okay. So now we're going to introduce a very important idea. Far more important than this? Yes, I'd say so. Far more important than what we're doing right now. So this is the idea of the limit superior and the limit inferior. So lim sup, usually abbreviated lim sup, and lim inf. So the limit superior, the limit inferior. Okay. Superior and inferior is not not praise or disparagement, but rather just the bigger one and the smaller one. So here we go. So you have a sequence. Let this guy be a sequence. Okay. We define, oh, and I should say that lim sup is sometimes notated like this, lim inf sometimes like this. Okay. Okay. So let E denote the set of all subsequential limits of S of n. Okay. So you look at all the subsequences and see, look at all convergent subsequences of S of n. So S of n may not converge itself, okay, but you look at all subsequences that converge, okay, and you call that you call that E. I'm sorry. You look at all the limits, and you call that set E. Okay. So it's a set of E is the set of all x such that S of nk converges to x for some subsequence S of nk. And then, so notice that this set E lies in the extended real numbers. Okay, so you could have sequences that converge to infinity or negative infinity. We're still going to include those in E if they converge to infinity, or if they converge to infinity or negative infinity. Okay, so we define the limit lim sup of S of n as the supremum of E, and the lim inf as the infimum. Okay, so let me give an example. So for example, if you have S of n is -1 to the n, the example that Anne put out earlier, right? Well, this sequence doesn't converge, but what kind of subsequential limits does it have? What is its E? In this case, E is going to be what? Can you make some subsequences that converge? Sure you can, right? Just like take the odd guys, take the odd terms, they converge to -1, take the even terms, they converge to 1, and that's it, right? Those are the only subsequential limits. So -1 and 1 are your set of subsequential limits, right? The lim sup of this is going to be 1, right? So lim sup, this sequence is 1, the lim inf is -1. So, so this is what if the lim sup and the lim inf are equal to each other? What would happen in that case?
Limit of sequences.
Then the limit would exist, right? Because then, yeah, that's right. So then, right, the subsequent, these things would be equal, right? And there would be only one subsequential limit, right? So yeah. Okay. So yeah. So if lim inf equals lim inferior, then the limit exists. So what we're going to use this for is there are theorems that you've seen before that rely on the limit existing. So like back in Calc 2 when you saw like root test and ratio test for convergence of series, those were phrased in terms of the limit, a limit. But it actually turns out that you can replace that with the lim sup. You know, as long as the subsequential limits are as long as you have a lim sup, then those theorems will still hold. So this is kind of a weaker version of the limit that still has the things that we want it to have. Okay, so here is the theorem, an important theorem regarding the lim sup. So characterization of the lim security. Okay. So so just as before, we have a sequence, and E, the set of subsequential limits. Okay, and yeah, okay. So first part is one, that the lim sup is itself a subsequential limit. And the second is that so that lim sup has a particular property. Okay, and that property is that whenever you take a number bigger than the lim sup, then there exists a time past which S of n is smaller than that number. Okay, so the way you want to think about this is, I think it might be better to phrase it like this. So for any epsilon greater than 0, there exists a time past which Sn is less than Sn plus epsilon. That's basically the same thing. Like, given any number bigger than Sn, there's a time past which everybody's smaller than that number. Okay. So here's your what am I writing here? Lim sup plus epsilon. Sorry. Okay, so you have your sequence, and then you have the lim sup. And what this is saying is that if this is the lim sup, then if you take anything bigger, then there's a time past which everybody's under that upper line. Okay, and if we were doing something like this for the lim inf, it'd be like something similar, right? If this were the lim inf, then given any number smaller, there's a time past which everybody's above that line, right? And you can see how the two of these together are basically the same thing as saying that, because if you have a limit, then what you're saying is that given any number bigger and any number smaller, you can chop the number between those lines, right? And so these lim sup and lim inf are basically like half limits. Okay, I think that's the best way to think about them. there's some sort of half limit, right? And if you've got both half limits, then you have the whole limit. Okay. So lim sup is itself actually a subsequential limit, and lim sup has this property, right? Has this half limit property, further. Any number satisfying both properties, both 1 and 2, must be the lim sup. Lim sup is the only number that has these two properties. That is, you can't have two numbers that both have those properties. Okay. So lim sup has these properties, and any number with these properties is the lim sup, right? So this is what we call characterization, right? It's a different way of thinking about the lim sup. Maybe let's think about this. Let's think about this one first. Why is it true that if you have two numbers that have these properties, then they must be equal to each other? Right. Let's think about uniqueness. Suppose two numbers p and q both satisfy 1 and 2. Okay, and they're not equal to each other. And let's say that p is less than q. Okay, so here's p, here's q, and they both satisfy this. Okay. If you look at this, well, the second property says that, given any number bigger than q, right, you can find a time pass which everybody's lower than that, right? And it also says that given any number bigger than p, you can find a time pass which everybody's lower than that, right? But let's think. So if you choose a number that's between them, right? Choose an x that's between p and q. Okay, you know that. Right, then the exists a time past which all S events are smaller than x, right? So there's this time past which everybody's smaller than x, right? But then q couldn't be q is not going to be a subsequential limit, right? But then q doesn't satisfy 1. Right. So, yeah. So lim sup is the only number, right? Is it the unique number that satisfies these numbers? Okay, let me erase this sorry. Is that all right? People copy this down? Kaylin's okay? Yeah? Okay. So, I wish we had like fancier boards. Like the boards where you can like switch boards and stuff. That's pretty handy. Okay. So let's so actually I forgot, or I didn't forget, but I didn't put it up. Rudin's notation is this. He uses E star as the set of subsequential limits. Okay. So if I just write E or E, if I write E or E star, it's the same thing. Okay. Okay. So let's do the first one that let's do the first one that the lim sup is itself a subsequential limit. Okay. So one lim sup actually is itself a subsequential limit. Okay, so proof. There's going to be three cases. Case one, and just for convenience, I'm going to notate this S star. So lim sup, I'm just going to notate as S star. Okay. So case one, suppose S star is negative infinity. Okay. In other words, right, so that's the lim sup of the set of subsequential limits, right? So if the lim, I'm sorry, that's the sup of the set of subsequential limits, right? Well, if the sup of the set of subsequential limits is negative infinity, well then, the set must be, the set of subsequential limits must just be negative infinity, right? Okay. So what does that tell you? That tells you that there exists a subsequence that converges to negative infinity, and you're done. Okay. Case two, suppose S is positive infinity, right? Right. In that case, the set of subsequential limits has no upper bound. Right. Has no finite upper bound. Right. And that tells you that the sequence is not bounded above. The sequence itself is not bounded above, right? And if the sequence isn't bounded above, then you can create a subsequence SNK that converges to positive infinity. Right. Is that clear? I hope that's clear. Okay. Okay. So in the third case, when this thing is real, we need to use a lemma. That E star is actually closed. Okay, so this is lemma 3.7 in the text. So what it's saying is that the set of subsequential limits of subsequential limits is closed. Okay. I'm not going to prove it, but let's just think for a minute why this makes sense. Okay. So we have some sequence, right? We have some sequence, right? And you're looking at the set of subsequential limits, right? So there are these points here. Each of these points, oops, right? There are these points here, and each of these points is a subsequential limit, right? So we know that there's some subsequence converging to these points. Okay. There's some subsequence converging to this guy. There's some subsequence converging to this guy, and so on and so forth. Okay. We want to show that that set is closed, right? So what does that mean? It means that it contains all its limit points, right? In other words, if you're a limit point of the set of subsequential limits, then you must be in the set of subsequential limits, right? Any limit point, so what we're trying to show is that any limit point of the set of subsequential limits is itself, right, is itself a subsequential limit. Right? Okay, so suppose you have some point here, and this thing is a limit point of the set of subsequential limits. Okay. Then you want to show that it itself is a subsequential limit, right? So you have this point here, P, say, and it's a limit point, so P is a limit point of the set of subsequential limits. Okay, and you want to show that you can create a subsequential limit that goes to it. Okay. Anybody have an idea of how that might work? So take some point, okay. Take some point S of n, okay, and I'm sorry, S of n1, okay. It has some distance to P, and okay. So now let's take half of that distance. Let's take half of that distance so that we exclude, if we don't hit this guy again, right? We know that P is a limit of the set of subsequential limits, right? So we know that there's somebody inside here who itself is a subsequential limit, right? Okay. Actually, let me take it even smaller. I'll take a quarter of the distance. Okay. So I know that there's somebody inside here who is a subsequential limit, right? So I use the quarter distance. That guy being a limit of a subsequence means that there's somebody inside there from his sequence, right? So I'll call that guy Sn2, right? And make sure that you can ensure that this index is bigger than this index by just going farther down the line, right? Okay. So call that guy Sn2. That guy is less than half of the distance of the previous guy. And then just iterate, right? Just iterate. So now you've got this distance, now you've got this distance, take a quarter of the distance. You know that this being a limit point means that there's somebody inside there who's a subsequential limit. It being a subsequential limit means that you can find somebody, et cetera, et cetera, et cetera. Right? Okay. Okay. So then in that way you generate a subsequence that converges to that P. So any limit point of the set of subsequential limits is itself a subsequential limit. Okay. So, okay, and that basically does it for you, right? That basically does it for you because look, right? S is the supremum of E, right? S is the supremum of E, which means that it's a limit point, right? So S is a limit point. S is in star prime, right? Which means that what we just said, S is in E star. so that proves the first part, right? That whenever you have a lim sup, it itself is a subsequential limit. Now let's get to the second part. Let's do the second part. Given any epsilon greater than 0, there must exist a time past which S sub n is less than S star plus epsilon. Okay, so here's S star, here's S star plus epsilon. We want to show that there's some time past which everybody's below. And we'll do it by contradiction. Okay, so suppose not, right? Suppose that for every n, suppose that there's no n that works, right? We're trying to find an n that works. Suppose all n's fail, right? Suppose that for every n you choose, there's an little n bigger than that guy, such that Sn is greater than or equal to S star plus E plus epsilon. Okay, right? So here's your time n, and look, for every n you choose, there's always somebody past n that jumps above the line. Okay. Okay. But that would mean that implies that there are infinitely many S sub n above the line. Okay, but if that's the case, then either they go off, if you look at those guys who are above the line, either they're unbounded or they're bounded, right? If they're unbounded, you can find a sequence that converges to infinity. You can find a subsequence that converges to infinity. So if those Sn are unbounded, then can create an Snk that goes to infinity. Right? If those Sn are bounded, then can create a convergent Snk that converges to something P that is bigger than or equal to S star plus epsilon. Right? All those guys are above the line, the S star plus epsilon line, right? And if they're bounded, then they lie in some compact set. And so you've got convergent, you can create a convergent subsequence. Right? But in either case, this means that we've got, in either case, we have a subsequential limit larger than S star. Contradiction. Right? S star was supposed to be the supremum of the set of subsequential limits. Okay, so any questions? Any questions? Okay, so yeah, this theorem basically showing that the subsequential limit is this sort of half limit, it will be really useful to us. There's one more theorem that I'm just going to state. So it's kind of obvious. So if you have two sequences, Sn, Tn, sequences, if there exists a time past which Sn is less than or equal to Tn, then kind of obviously the lim sup of the smaller guy is less than or equal to the lim sup of the bigger guy, and the lim inf of the smaller guy is less than or equal to lim inf of the bigger guy. So that seems kind of trivial, I hope, but this will also be useful. Okay, so yeah, this it seems kind of more amorphous than the notion of limit, but like I said, this is really what will be useful when we start talking about series. So next class we're going to go into series and basically prove everything that you've seen you saw before in Calc 2 using limit. Okay, that's it for today.